Swayam Prabha. Digital India. Educated India.
Welcome to the fluid mechanics class. We are in the topic fluid dynamics. So in the last lecture of fluid dynamics, we discussed various aspects of Reynolds transport theorem. We derived how it is linking the system and control volume approach, as well as we also discussed the linear momentum equation that has been derived based on the linear Reynolds transport theorem, and we also saw various applications of the linear momentum equation. So in today's lecture, we will see equation of motion for real and ideal fluids. We'll also see Bernoulli's equation and how it is applied to various problems. Now, when we talk about equation of motion, so basically it is the law of motion. So the moment we talk about law of motion, we remember the Newton's law of Newton's second law, so which says that force is equals to mass into acceleration. So now we have already seen that how the acceleration is derived, how the total acceleration is derived based on temporal as well as convective accelerations. Now mass is the mass of the particle or the fluid element. Now what are the forces? What are the different forces that are going to act on the fluid element? So if we look at the forces that are influencing the motion, we can name major forces that are going to act, which is gravity or the body force. Then there is a pressure force which can act, okay, which is fluid pressure. Then there is molecular viscosity or the viscous force that is going to act. We have already seen that how the viscous force is going to act, and the tau is equals to mu du by dy, so viscosity is going to play a major role. In addition to that, there is a surface tension force which is going to act. Due to compressibility, there will be some force. When there is a turbulence, there will be Reynolds stress which will be generated, and that is also going to act on the fluid motion. So all these 6 different forces that are going to act can be broadly classified into 2 categories. We can take it as body force or we can take it as a surface force. So those which are within the body, they are acting, so we can take it as body force. If something is acting on the surface, we call it as a surface force. So now among these 6 different forces that we have listed here, we are not going to consider some of the forces right now, because right now we are not talking about the turbulence. So Reynolds stress we will not talk about. So right now we will not consider the Reynolds stress. It will come only when we will talk about the turbulence. So effect of turbulence is not in picture right now. As we are also assuming the fluid as incompressible, and most of the hydrodynamic problems or the applications in hydraulics are using water or a liquid which is mostly incompressible, or we can assume that as incompressible. So the compressibility is neglected. So in that sense, we can neglect the compressibility and assume incompressible flows. As we are talking about large scale flows, we also can neglect the surface tension. So what we have is the gravity force, okay, the fluid pressure or force due to pressure, then the viscous force. So 3 different forces we are going to consider at this moment. Okay, now let us look at these forces. So once we are looking at these forces, let us take a fluid element first. So let us consider a fluid element which is having dimension of dx, dy and dz. So this fluid element is going to have all these forces acting in that element. So as we have already discussed, there is going to be gravity force. So that is the weight of this fluid element that is acting on it. And in this case, if we are taking vertically downwards, the weight is going to act vertically downwards. So volume multiplied by unit weight will give you the weight of that element, fluid element. Now what is the next force? There is a pressure force which is acting on the surface. Now here you can see I have shown here the Px which is acting in the x direction. So the pressure that is acting in the face, that is this one, which is nothing but your dy dz, and there is a pressure acting as Px, the left side of the face. Now similarly, just on the other side, opposite side, there will be also a pressure acting, and if we say that pressure is Px here, over a distance the pressure would have changed, and the rate of change is dou Px by dou x. So over a distance of dx, the change is going to be dou Px by dou x multiplied by dx. So the Px plus this component is going to be the pressure which will act on this surface. Okay. Now the pressure is, I think there is a mistake here. It should be acting towards the fluid element. Okay, pressure is going to act always towards the fluid element. So if we look at, the pressure is going to be acting towards the fluid element. Okay, so that is the pressure force that is acting. Now pressure integrated over the area is the force that is going to act. Okay, all right. Now what are the other stresses? There are surface shear stresses or normal stresses that are going to also act. Now there could be normal stresses which is shown like this, which is sigma x. Okay, now sigma x is the normal stress that is acting in the x direction. Now similarly, there will be sigma y and sigma z acting in y and z directions. In addition to the normal stresses, there will be some shear stress which will act, because if there is a fluid is in motion, there will be some motion between the elements. They may not be moving with the same velocity. So if there is a difference in the velocity or different in the motion between two different fluid elements, then there is going to be some shear. So these shear stresses can be represented using the notation tau. So we have on this face, let us say this dy dz face, we have shear stress that is acting, which is going to be tau xy and tau xz. Okay, so it is the shear stress that is acting in the direction of in the x direction, or in the on the face of face perpendicular to the x direction, but the force is acting in the y direction, here is acting in the z direction. So we are writing tau xy and tau zx. Similarly, there will be opposing forces, shear forces, that will be acting on the exactly other side. So here you will have some force which will be tau xy acting in the other direction, just opposing the tau xy force. Okay, so similarly, if we look at this face, which is dx and dy face, on this face we can see that the shear stresses are acting, that are tau zx and tau zy. All right, so now all these forces are acting. Let us sum it up and apply it to the Newton's second law. Okay, so all the forces, but before that I'll just quickly explain that the subscript for the tau, the first subscript denotes the direction of the normal to the plane on which the stress acts. So that is, let us say we are talking about tau xy. So in case of tau xy, x represents the direction of the normal to the plane on which the stress acts. Okay, the second subscript y is going to denote the direction of the force which causes the stress. Okay, now there is a force in the y direction that causes this shear stress, so that's why it is acting in a face which is perpendicular to x direction, that is tau x, and due to the force in the y direction, that's tau xy. All right, so all the notations which are written is according to this. All right, now let us write down the equation. So if you see this equation, we have written the first, on the left hand side of this equation, we could see that this is nothing but your mass into acceleration. Okay, so we have taken the volume out, so this is mass into acceleration per unit volume. Okay, so you can write down dou rho u by dou t plus u dou rho u by dou x plus v dou rho u by dou y plus w dou rho u by dou z. Okay, now let us write down the forces that are acting. First one, we know there is a body force or the gravity force. So body force is the G or rho G gamma acting on the volume. So because we are taking per unit volume, so it is rho Gx. So the gravity acting in the x direction. Okay. Don't worry about whether the gravity is going to act in the x direction or not. Let us say there is some gravity which is acting in the considered x direction. So let us write down Gx. If it is 0, we can substitute 0 at a later stage. Right now, let us keep it. So rho Gx plus the stress that are acting. So we are not writing the pressure here, rather we are writing the stress. So stress dou sigma x by dou x. So that is the stress, normal stress that is acting on the fluid element. Okay. Now, what is the why this dou sigma x by dou x is written? If you compare this left side and right side, you will be able to find out the net force that is going to act in this direction due to this normal stress is going to be only dou sigma x by dou x. Similarly, the shear stresses are going to act, that is going to be dou tau yx divided by dou y plus dou tau zx divided by dou z. So these are the ones which are going to act in the x direction. So here if you see tau zx is shown here. So this is in the x direction. Similarly, I have this face which is not shown, all the notations are not shown, but there will be a component which will be tau yx. So the plane perpendicular to the y direction is this, and on this the force that is in the x direction will generate a shear which will be tau yx. All right. So if I just want to show you typically that at this point there will be tau yx. Okay, and there will be stress acting in the other direction, that will be tau yz, and there will be normal stress which will be sigma y. Okay, so let us not worry about all that, you know already. So let us consider this force that is in the x direction, tau yx. All right. So once we have written down all the stresses that are acting on this, now let us see how these forces we can. I think this is the same equation, there is no change. So okay, this is in the y direction. All right, so we have written this equation in the same way in the y direction, and similarly you can also write down the equation in the z direction. So now you could write down the forces or fx, fy, fz, that is the summation of forces in x, y and z directions that are equals to mass into acceleration in x, y and z directions. Okay, so now once we have this, if we say that this flow or the fluid is a Newtonian fluid, okay, so the fluid that we have considered is a Newtonian fluid. What do you mean by Newtonian fluid? It obeys the Newton's law of viscosity. So tau is equals to mu du by dy. All right. So the moment you start applying any amount of stress or force, it starts deforming. So there is a linear variation. So tau is equals to mu dou u by dou y, dou u by dou y. Okay, so considering this is a Newtonian fluid, now if we write down the equations or expressions for the shear stress tau, which you know already, tau we are writing, let us say tau yx. Okay, so in all three different directions, tau xy or tau yx, as I said, they will be opposing, so they are going to be same. So if we write down the equation for tau xy, it is going to be mu dou b by dou x plus dou u by dou y. It is not only due to this, because the total shear is due to two different components, as well v as well as u on this face. Okay. Now in the plane that is perpendicular to the z, okay, you have tau xy or tau yx, isn't it? Now we know that similarly we can write down the equations for tau yz and tau zy, which is going to be mu dou w by dou y plus dou v by dou z. If you keen look at this, this is zy or yz. So you have w, y and v, z. So similarly, if you have zx, tau zx, you have dou u by dou z plus dou w by dou x. Okay, and these three terms can be now used to write down or substitute some of the parameters in the equation that we have written before. But now before we go to that, let us look at the stresses that are acting in the normal directions, that is tau sigma x. So sigma x, sigma y, sigma z, based on some derivations which I am not going to really explain here, we can find out sigma x is equals to minus p, or you can write down px minus p plus 2 mu dou u by dou x. Okay. Similarly, sigma y is equals to minus p plus 2 mu dou v by dou y. Sigma z equals to minus p plus 2 mu dou w by dou z. Because the pressure here, we assume that it's an elemental fluid and p is going to be equal on all sides. So it is p. Okay. So now, considering this, we can write down all these terms tau as well as sigma in terms of pressure and velocity u, v and w. Why are you doing these things? What is the need for this? Now I'll quickly take you back to the previous expression. Now you see this equation. What we are trying to solve? We are trying to solve the fluid motion. Okay, this is the equation of motion for fluids. So here, how many equations do we have? We have three equations. And how many unknowns do we have? If you look at what are the unknowns here, u, v, w, the velocities in each directions, u, v, w, three directions, x, y, z directions are unknown. So now here, what are the other unknowns that we have? On this side, we have only u, v and w. If you look at the right side, you have sigma x, sigma y, sigma z. So you have three more unknowns that are the normal stresses in all three different directions. So we have six unknowns now. Now look at this tau. So tau yx is equals to tau xy. So we will assume they are both are same. So let us say this is 1. So we have similarly tau zx, tau xz and tau xy, tau zy, tau yz. So we have three more shear stresses. Okay. So this, although there are six terms here, but there are equally opposing for shear stresses. So we will consider only one. So three shear stress which are unknown, three normal stresses are unknown, three velocities are unknown. So we have 9 unknowns, and you know that you need to have that many number of equations to solve whatever number of unknowns that you have. So if you have 9 unknowns, you need 9 equations, but we have three equations. So if we can convert or represent these unknown terms in terms of u, v and w, then our problem will be simplified. We can reduce the number of unknowns. So that's what we are doing here. We have this tau that is represented in terms of u and v. Similarly, sigma is represented in terms of pressure as well as velocities. So now these 6 unknowns we have represented using 4 unknowns now. So already 3 unknowns, same u, v, w. So additional 1 unknown is still remaining, that is pressure. So right now altogether in the equation we have 4 unknowns, u, v, w and pressure. So now let us write down this equation, new equation, based on this, substituting these values of tau as well as sigma. Okay, so this is my equation in the x direction. I have written the equation in x direction. Let us look at that. So we had this equation, that is dou rho u by dou t plus u dou rho u by dou x plus v dou rho u by dou y plus w dou rho u by dou z, that is equals to rho gx plus dou sigma by dou x plus dou tau yx by dou y plus dou tau zx by dou z. Now in this, let us just pull those equations which we had already written for the tau as well as sigma. Now if I take the first term, that is sigma, I can write down sigma x equals to minus p plus 2 mu dou u by dou x. Similarly, I can substitute the value for tau yx and I will take that from here. and again for tau zx I'll take the value from here. Alright, so let us write down. So I'm not writing the left hand side of this term, I'm going to write only the right hand side and see how we can rewrite the equation. So if we look at, you have this rho gx here. Now if you substitute sigma x in terms of minus p plus 2 mu dou u by dou x, you can write down minus dou p by dou x plus 2 mu dou square u by dou x square. Alright. Now similarly, let us substitute in the term tau yx. What is tau yx or xy? That is this mu dou b by dou x plus dou u by dou y. Now if I substitute mu dou b by dou x into dou by dou y, so dou square v by dou x dou y plus mu dou square u by dou y square. So now by substituting tau zx, I can write down mu dou square u by dou z square plus mu dou square w by dou z dou x. Okay, so this is the modified equation that we have now. All right, now we can take this equation and start solving, but let us see if we can simplify that further. So if you just rewrite this whole thing again, I can keep this rho gx minus dou p by dou x plus I have taken this mu here and all these terms which are having dou x square, dou y square, dou z square, I have put them together. So it is dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square. Putting them together, I can write down this expression. Now what I have is this one, that is mu dou square u by dou x square plus mu dou square v by dou x dou y plus, I think there is one plus required here, mu dou square w by dou z dou x. Now here if you look at, in all these three terms you have a dou by dou x. Now let us take that out and see what is happening. So if you look at, if you take it out, you can write down mu dou by dou x of dou u by dou x plus dou v by dou y. I think it is something wrong here. So it should be dou v by dou y and it is dou v by dou z. Okay, so this plus is not required. This should be dou v by dou y and this is dou w by dou z. So now once we have this expression, you can see that this equation or this part of this equation is nothing but your continuity equation, and we know that for continuity to be satisfied, this term has to be 0. So this term is 0. Now this whole thing is eliminated. Now what we have finally is only this term, which is nothing but rho gx minus dou p by dou x plus mu dou square u by, again there is another mistake. This mu should not be there. We have taken it out. So mu dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square. All right. So we have this equation which is now going to be considered. So what we have right now finally, we have a gravitational force or body force, then there is a force due to the pressure and there is a force due to viscosity. So this term is nothing but your viscous force, this is pressure force, this is your body force. So now if we rewrite the expression that we wrote in the beginning here, okay, so by substituting this modified term, if we put it, this is what is your equation now. So we can write down dou u by dou t. See here we have taken the rho out, so we divide by density again. Okay, so we had already divided by the volume. So now if we say that, okay, per unit mass, what is the equation? So acceleration per unit mass. So this equation, which will be dou u by dou t plus u dou u by dou x plus v dou u by dou y plus w dou u by dou z is equals to minus 1 by rho dou p by dou x plus gx plus mu by rho dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square. All right. So this is what is your equation of motion which you have derived now. All right. Now, once we have derived this, let us look at a compact form and let us look at the expressions in all different directions. So what we have derived is for the x direction alone. Now, if I write down this equation in x direction, this is what is the equation which we have already derived. Now, in y direction, if you look at, we have written down, and the changes, if you observe, it is dou v by dou t. Here, everything remains same, only the u changes. So dou v by dou t, dou v by dou x plus v dou v by dou y plus w dou v by dou z is equals to 1 by rho dou p by dou y, the pressure gradient in the y direction. All right, and the body force in the y direction. And here we are writing the viscous force. So in this viscous force, if you see, all the other terms remain same except the velocity v is going to substitute the u that has been used here. Okay, so dou square v by dou x square plus dou square v by dou y square plus dou square v by dou z square. All right, so similarly we can write down the expression in z direction. So all three equations are the equation of motion. Now if you again finally look at this, we have again three equations and we have four unknowns. We have u, v, w and pressure. So we know the density, we know the viscosity of the fluid, okay, we know the gravitational acceleration, all that we know, but what we don't know are the velocities and the pressure. These are unknowns. So we need to have one more equation that can help us to solve four unknowns that we have from this set of equations. So to do that, we add this continuity equation to get the full set of equations. So all this set of equations can be used to solve the four unknowns and get a solution for any fluid flow problem. And this equation is nothing but your Navier-Stokes equation. So Navier-Stokes equation that has been derived to solve the fluid flow problems. And you see here we have considered the body force, we have considered the pressure force, we have considered the viscous force. So to note it down, Navier-Stokes equation do consider the viscous effect of the fluid. And the moment we say that fluid is viscous, we are basically telling that the fluid is real fluid. So Navier-Stokes equation is going to solve the real fluid flow problems. Okay, we have already seen earlier what is the difference between ideal fluid and real fluid. So the moment we have considered the viscous effect, we are mostly talking about the real fluid flow scenario. So the Navier-Stokes equation is capable of solving that. All right. Okay. Now, having understood this, we can slightly compact this whole set of equations to quickly remember that. Okay.